on this computer. All right. Hello. Welcome back to Chemistry 2330. We're going to finish up our last chapter before our next test, which is chapter 11. We're going to do goal number 3, which is carbon NMR, and then I'll have time to do a review. I've downloaded the review from Canvas, and I'll be going through there. I'm going to focus on our stuff since the last chapter, which is chapters 7, 8, 9, 10, and 11. Okay, so that's what we're going to focus most of our time on in the review, but you might want to go back and remember how to name things or remember what some functional groups are. Obviously, the most common functional groups we've gotten to the alcohols, but we did learn something about amines and we learned something about carboxylic acids when they're attached to benzene rings. So that benzene nomenclature will become important. Okay, so what I wanted to do right now is to remind you that we have a test coming up. It will be a top hat test, and it will be on Tuesday, April 6th. Tuesday, April 6th, okay? At this time and day, don't come to the Zoom meeting, just go straight to Top Hat. The test will open up for you. You'll have 80 minutes to answer the questions. Unless you have an ODS accommodation, then you'll have your extra time. And then you'll go ahead and submit it, and we'll curve it and see where everybody stands. Okay, any questions about the exam and or what we're going to do today? Okay, well, let's go ahead and get chapter 3. Goal 3 of chapter 11. So in chapter 11, we are talking about spectroscopy. And I like talking about spectroscopy. In fact, I would almost want to start with spectroscopy because I think that spectroscopy proves to us that these chemicals are real, okay? So we can see what kind of types of bonds we have with the IR spectroscopy, right? So we can see that we have a single bond, a double bond, or a bond to hydrogen. So that's what IR spectroscopy is telling us. It doesn't tell us really how they're hooked together, but it tells us where they are. In proton NMR, we learned where the hydrogens were based on their shift because of what their proximity to another group would make them shift up and down the line there. And we also saw that the number of hydrogens nearby. So with IR and NMR, you should start being able to piece the different fragments of the chemicals together and getting them in the correct order. Okay, so on our goal 3, we're going to add another piece here. And in proton NMR, we were only looking at the hydrogens. In spectroscopy, we were only looking at individual bonds. Okay, in carbon-13 NMR, we're looking at the carbon backbone. And the carbon backbone is going to have the same kind of things that we have shift that shows us that in fact, they shift in about the same way. The ones that are more aromatic or have more double bond character are further down than the ones that are not. And we're going to see that shift. Okay. So in proton NMR, we had spin, which is splitting, position, intensity, and number of peaks. Okay. In carbon NMR, it's a little bit easier because we only have to worry about 2 of those. Okay. Now, just to remind you, we're talking about having the magnetic moment of our nucleus, and we have to have an odd number of neutrons and protons in our nucleus such that we can get this unpaired, canceled out particle that gives us aligns in the magnetic field and lets us see it when it relaxes down and emits electromagnetic pulse. Okay, so but in carbon NMR, we have some issues. First of all, in proton NMR, we have hydrogen 1. That's the most common element. That's the most common isotope of hydrogen. So it has a very high concentration. And so it's very easy to see. It's over 90, it's about 99%. So it's very easy to see when you get those very clean, very strong signals, okay? But carbon-13 is a minor isotope. Carbon-12 is the major isotope, the one that's 98% of it. And then there's only about 1.1% of this heavier, one extra neutron, heavier carbon, okay? So that means that we have a very small percentage of it. And but what this also means is that we don't worry about splitting, because we're never going to have two carbons close enough together to see splitting, or if we do see splitting, it is so small we don't notice it. Okay, so that brings us down to intensity. Because again, it's such a low concentration, we actually don't worry about the intensity. So all we have to care about is the number of unique signals, so the types of carbon, and then the shift of the carbon. And so the carbon NMR is going to have one peak for each type of carbon, and then they'll shift up and down depending on what is attached to that carbon. So proton, we had those four things to worry about: spin, position, intensity, and uh, spin, position, intensity, and number of peaks. Here, all we care about is number of peaks and position. Okay, so now we have to look at carbon-13 kind of like we saw with the proton NMR, in the fact that we need to figure out what non-equivalent carbons are and what equivalent carbons are. Just like we did with hydrogen, you start moving out and seeing, okay, this carbon has two carbons attached to it, and this carbon has a chlorine attached to it. So those must be different carbons. So we have to use that same rule of figuring out which are different, okay? So when we're doing this, we actually have to be able to assign how many we have. And that will know how many peaks we should see in there, okay? Now, most of the time, because hydrogen and the proton, I'm sorry, and the carbon actually can see each other, we actually run in the experiment, so we take away any splitting from the hydrogen, so we get individual single peaks for each and every non-equivalent carbon. Okay, so let's go and look at something that has different kinds of carbons. Okay, so the first thing we do when we look at a structure is we figure out how many different types of carbons we have. Okay, so this carbon right here is the only carbon with three other carbons attached to it, and it's also the only one with the OH. So I'm going to say that's a unique carbon. That's the only one like it in there. Okay, so then let's kind of move out from there. We have a CH2 here bonded to this carboxylic acid. But hey, we have the CH2 here, and it's also bonded to a carboxylic acid, and it's bonded to the same type of carbon. So those become equivalent carbons. So we're going to get one peak for this here. Okay. Now you're saying, oh, well, look, we have three carboxylic acids. They're all the same. They're not all the same. We have a carboxylic acid that's attached to a CH2 group, a carboxylic acid that's, hang on, let me switch colors here. We have a carboxylic acid attached to a CH2. We have a carboxylic acid attached to a carbon with no hydrogens on it. So those are not equivalent. See, there's a different connection between them, and so they're not equivalent. But this one over here is. This one has the same attachment. So that means we're going to get one peak for these two here. Okay, and that means that our last carbon here, this carboxylic acid attached to the carbon with the oxygen on it, is different, and we're going to get another peak here. So we just found all the unique peaks by how they're connected together. So we're expecting to see a total of 4 peaks on our NMR. Okay, so let's look and see if we see those 4 peaks. Okay, so let's expand up here. And if we look here, we have, oh, this big, huge, horrible peak right here. Well, it turns out this is the solvent right here, and we've marked it as solvent. Usually if there's a solvent we're using, it'll show up, and what we'll do is we'll just kind of ignore it because we just need to know it's there, but we don't want to count it as a peak. So we're going to count our peaks. We have 1, 2, 3, 4. So we figured out that we had 4 unique carbons, and now we have 4 peaks in our NMR. Notice that they're all singlets and they all are of varying intensities. Okay, so we only have to worry about single peaks. Each single peak is a unique carbon. Now let's figure out shift. Okay. So when we're figuring out shift, we want to use the shift table that's down here, and it follows some of the general trends that we saw in the proton NMR. The sp3 hybridized carbons are first, closest to zero, and then an sp3 hybridized carbon with an oxygen or a nitrogen or a halogen. And then the sp2 hybridized carbons. And then we have a new type in this. We have a carbonyl, because carbonyls don't tend to have hydrogens on them, so we don't see them by NMR, but they do have carbonyls, and they're shifted much, much higher. So we can imagine that our C double bond O, all of these are, above 160, and some of them even go above 200. So if carbonyls are the ones that are going to be shifted that high, let's go back and look at our proposed structure here. Okay, so we have a carboxylic acid here and a carboxylic acid here, and they're different. Okay, so that carboxylic acid, of course, is a carbonyl with an OH on it. And so that's probably these two peaks right here, right above 160, but below 180. So those are our carboxylic acid peaks. So we've identified two of those carboxylic acid peaks. It turns out that the one that is bonded directly to this carbon with the oxygen on it is the one that shifted further up. I wouldn't want you to try to discern that. I just want you to know that both of those are going to be in that region. Okay. Then the other two peaks we have are this carbon with the oxygen on it, and then this carbon with two carbons on it. So among those, which is going to be shifted further to a higher chemical shift number, a higher number? Is it going to be the one that has the oxygen on it, or the one that has two carbons on it?
The oxygen?
That is correct, because adding your electronegative atoms like nitrogen, oxygen, and halogens shifts it further up than if it was just a regular hydrocarbon, which means that our last peak here, this is our last peak is identified as the lowest down, the closest to zero. This is going to be our red peak here. And then these are going to be our two other peaks. Turns out this one right here is our higher one, and this one right here is our lower one. So just like we did in hydrogen, we wanted to identify the unique types of carbons we have, then look at what's attached to them and have that general shift in there. So remember, in proton NMR, the most like a methyl group in hydrogen is our lowest number. And then so 3 hydrogens and then 2 hydrogens and 1 hydrogen, all on sp3 hybridized carbons, is our lowest. Then as we move up, we're going to see things attached to oxygens and nitrogens and halogens. And then above that is things that have sp2 hybridization, which it would include benzene rings and double bonds. And then above that were the carboxylic acids and aldehyde hydrogens. So we'll see that same kind of trend as they move up. And so in our carbon, we have our most hydrocarbon-like stuff here at the lower end, things with electronegative atoms attached to them, and then things that have carbonyls are going to be above 160. So benzene and stuff would show up in that 160 range as well. Okay. So let's predict the number of signals for each of these compounds, just like we predicted the number. And I also want to play with the relative position of these. Okay. So let's look at this first one here. And in this first one, we have this right here. And so if we looked at this in proton NMR, we would have two peaks, because we have the CH3 that's attached to the carbonyl, and we have the CH3 that's attached to the oxygen. Okay. So, but I'm going to tell you, we don't have two peaks on this one. We're looking at the carbons. We're looking at the unique carbons. Okay. So in this case, we wouldn't worry about the carbonyl in proton NMR because there's not a hydrogen on it, but we have to worry about it here. So we have the methyl group here attached to the carbonyl. That's going to be our one peak. We have our carbonyl. That's going to be our second peak. And we have our carbon with our attached to an oxygen and 3 hydrogens as our third peak. Okay. Just based on that, we're going to have 3 peaks. Okay. But now let's predict the position based on where they are and what's attached to them, okay? So this is an sp3 hybridized carbon without an electronegative atom. This is an sp3 carbon with an electronegative atom, and this is a carbonyl. So what I think is that the 1 peak is going to be closest to 0. The 3 peak is going to be next, and then the 2 peak is going to be way up above 160. Okay. So do you see how we're picking out unique carbons and then getting their relative position just by what they're attached to? Okay. All right, let's do one.
I have a question real quick. So the 1 peak, so the sp3 hydrocarbons, that's the lowest of 0, and
Yeah,
then the hydrocarbons attached to an oxygen are higher because they
right,
oxygen is more electronegative.
correct.
Okay.
And then the carbonyl is the highest because of that double bond with the oxygen.
And this is based off of like peaks in like the spectrometry chart.
Correct. And if you'll see that on this right here, it's agreeing with those things, right? Oh, come on, there we go. That the most like sp3 hybridized are going to be the lowest. The sp3 hybridized with electronegative atoms are next. The sp2 hybridized alkenes and aromatics are next. And then we have carboxylic acids. And the carboxylic acids are lower because they have a carbonyl plus an electronegative atom on them, and then a carbonyl without electronegative atoms. So ketones and aldehydes are higher. So you see how that trend is following with what we saw, the basic shift pattern in proton NMR as well. All right, so let's do the same thing here. We're going to predict the number of peaks and their relative position, okay? So let's see, we have a methyl group and a methyl group, but they're different because this one's attached to a carbonyl and this one's not. So that means we have at least 2 peaks, 1, 2. We have a CH2 and a CH2, but are they the same? One's attached to a carbonyl and one's attached to a methyl group, so they're different. So that's going to be 3 and 4. And let's not forget that carbonyl. That's going to be number 5. Okay. So in order, we're probably going to have, this is going to be the lowest number, next, 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 and then this is going to be the one that's going to be above 180 ppm because it's the one with the carbonyl. And so this is most hydrocarbon-like, this is the next most hydrocarbon-like, this is the next most, and then this last one over here is going to be just a little bit higher than them, but that carbonyl is always going to be the highest peak. So if we looked at a spectrum and it only had 4 peaks, it can't be this compound. If we looked at the spectrum and it had 5 peaks and it had 4 of them down low and 1 of them way up high, that would be consistent with what we expected to see from this. 4 peaks in that lower range, that sp2 hybridized carbon, I'm sorry, sp3 hybridized carbon, and we only have 1 thing that's in that carbonyl range. Okay, so let's do one more. Now, when we did this in proton NMR, we found we had symmetry, okay? And so we only had 2 peaks of different types in the proton NMR. But here, we still have symmetry. But we will have 3 peaks because this is equivalent to this. So that's going to give us 1 peak. This is equivalent to that, which is giving our 2nd peak. But don't forget the carbonyl. A lot of people will forget the carbonyl as our 3rd peak on there. And so we should see 3 peaks in the proton NMR. So if I gave you a proton NMR and I said, which of these 2 compounds was it? And it had 3 peaks, you would know it would be this compound. If it had 5 peaks, you know it would be that compound. Or if it had 4 peaks, you'll know it's none of these compounds. Okay? So do you see how we use carbon NMR to help look for connectivity and look for different types of carbons by the spectroscopic method?
I have a for the clarification question. When you're talking about upfield and downfield, upfield's closer to 0 or further from 0?
Upfield is closest to 0.
Closest to 0. Okay, thank
Infield
you.
in a baseball, you know, it's you're trying to get closest to the home plate. That's upfield.
Okay.
Downfield is further away.
Okay, thank you. I think I was doing it backwards on the homework.
The left.
I have a question.
Yeah.
So for C, so then let me see here. So the two methyl groups, the CH3, they would be closest to 0. Then the CH2s, and then the carbonyl would be farthest away. Correct?
Correct.
Okay.
Yeah. So carbon NMR is kind of neat in that way because you'll know, hey, this one has 4 different peaks. We only have 3 different peaks in this compound, 3 different peaks in this compound. This is the only compound with 4 peaks. That must be my answer.
I have a question too.
Yes.
For B, why is the hydrocarbon on the right side of the carbonyl higher or lower than the left one?
Okay.
That's
Why
attached to it.
yeah, why is this one different than this one? Yeah, it's attached to it's attached to the carbonyl, which shifts it up some. Not too much, because it's still going to be in this range of 0 to 50, but this one's just a little bit higher. But all 3 of these are going to be, you know, in that all of the ones with hydrogen on them are still going to be in that 0 to 50 range. But this one's just, I'm just happen to know it's a little bit higher.
Is the CH3 higher than the CH2 attached to the carbonyl?
No, the CH3 is going to be closer to 0 because just like in hydrogen, the CH3, the hydrogens were closest to 0, the CH2s were next, and then the CHs were higher. So the more hydrogens you have, the closer you are to 0.
Oh, okay.
And it works the same in carbon. It's the more hydrogens the carbon has on it, the closer it'll be to 0.
Awesome, thanks.
And the cool thing in carbon NMR, we also use the TMS, the tetramethylsilane, as our standard for 0. And that has 3 hydrogens on a carbon attached to a silicon. And so that's our 0 ppm, and everything else is above it. So here's some more shifts that we can help to kind of guide this. But remember, those principles that I talked about are the same right here. So when we look at our CH3s, the carbons that have hydrogens on them and only hydrogens on them are going to be shifted lowest, closest to 0. Just taking one of those hydrogens off makes it shift up to above where we see the methyl group by itself. So see how it's shifted above, but it's still in that range, 0 to 50 range. If we take it and take one of the more hydrogen off, it shifts it above, just like it did in proton NMR. Okay. By adding halogens, right here, we go a little bit of a shift up to where even chlorine, the smaller the ion is, the higher it goes. So it shifts it up. So these are the electronegative atoms shifting it mostly above that 50 ppm range. Now we have oxygens here, which is above that 40 to 80. Triple bonds are actually about the same, where in the alkyne hydrogen was below the hydrogens of the, upfield from the hydrogens of the alkenes. And the alkenes are, again, higher. In this case, it's 0 to 100 to 150. So we're following the same shift trend we saw in the carbon, in the proton. Okay. When we get to benzene rings, we'll start to see peaks in here. And interesting note, if R is H here, we have one type of carbon because it's a resonance structure. It's going around and around. So we'll only see one peak. But if you put a substitution on here, right here, Now we have different unique peaks because we have the one peak, which has the thing bonded to it. These are equivalent, those are equivalent, and then that's there. So we might end up with 4 peaks just by adding one thing to benzene ring. Okay, so if you have to do an NMR of benzene, keep track of where the substituent is to make sure you have the correct number of unique carbons. Okay, now all the carbonyls are above 150. And so the ones with electronegative atoms, the ester, the amide, and the oxygen here are between 160 and 185, okay? However, the aldehydes and the ketones can go above 200. Those are the only ones that are that high, is the aldehyde carbonyl and that ketone carbonyl. Okay. And in proton NMR, the only thing we see above 10 is this carboxylic acid hydrogen. Okay, so that is carbon NMR in a nutshell. You're looking for number of unique carbons and the relative position from 0 up using that same philosophy we saw in hydrogen. Okay, and that is goal number 3. Okay, so now I'm going to shift gears and go ahead and pull out the review, which is right here. Okay, so on the review, it has chapters 1 through 11, just because I want to make sure you don't forget a couple of things. One thing you don't want to forget is if your functional group names, I would study that a little bit because functional group names are important for the system. And don't forget your nomenclature. We talked about alkenes and alcohols and stuff like that, so we want to make sure we don't forget that. Plus your acids and bases. Okay. So those are the nomenclature rules that we have, and you'll still need a little bit of nomenclature because we did name the alcohols and we did name the amines and we named the carboxylic acids. Okay. I'm sorry, we named the benzene derivatives. So that got us up to chapter 7, which is where we're going to, no, chapter 7 we tested on last time. So that brings us up to chapter 8. Okay. With chapter 8, we started with alcohols. And number 1, don't forget to name them. Number 2, we saw that they had hydrogen bonding. And that's what gave them the difference in properties by having the idea that it can hydrogen bond in between molecules. And that gave rise to higher and boiling points and melting points. But let's talk about some of the reactions we have with alcohols. We can do a reaction with an alcohol where we remove the OH and turn it into an alkene. The requirement there is that you have to have a hydrogen on a carbon adjacent so that it can form that alkene. And this process is called dehydration. And we found out that in the primary alcohols, you had to heat it up really, really high to get that elimination to go, because it kind of forms a partially positive charge in the mechanism. And so it's very hard to do with a primary alcohol. It's easier to do with a secondary alcohol, and the tertiary alcohols do it much more readily than anything else. Okay. When you form these alcohols, the hydration of alcohols, you want to form the more stable alkene, the Zaitsev product, which is the one with more double bonds on it. We're going to see that a lot in the dehydration. If you have a choice between 2 substituents on an alkene and 3 substituents on an alkene, the major product is going to be that substituent on the alkene. Okay, this is wrong on my slide here. This is tertiary alcohol right here. The other thing we can do is oxidize them down to have carbonyl compounds in them. So if we have a primary alcohol, we can get an aldehyde, but only if we use the pyridinium chlorochromate, or PCC. Okay, we can only stop at the aldehyde if we use PCC. But if we use something stronger, like chromic acid, we will get a carboxylic acid. Okay, so those are the 2 things we can get from primary alcohols. Secondary alcohols only give ketones with either reagent. Both reagents will convert secondaries to ketones. In tertiaries, because there's no hydrogen on a carbon next to them, because there's no hydrogen on the carbon that the OH is on, there's no reaction. So tertiary alcohols don't react to oxidation. Okay. Now, within that chapter, we also talked about epoxies, and we talked about ethers. Okay, most of the ethers are very, very stable, have no reactivity at all, except for this three-membered ring called the epoxy. And we found out that we could open that ring up with any nucleophile, and that would generate an OH from the epoxy itself and an attachment by whatever other nucleophile it was. So in the case of an amine, it'll give you an amino alcohol. In the case of water, it'll give you a diol. In the case of any other nucleophile, it'll give you that functional group plus the alcohol. Okay, so that's the only ether reaction we have in this chapter. Okay, that brought us to benzene and its derivatives. The first thing you got to remember about benzene is the 4 rules for aromaticity. Must be in a ring, must have p orbitals on each of the rings, and must be flat, and it must have the correct number of electrons. And the correct number of electrons is 4n plus 2. So that's 2, 6, 10, etc. Okay, if you want to just remember 2, 6, 10, those are the requirements there for aromaticity. Okay, now when we got to aromaticity and benzene, we had special names. So knowing the special names like benzene, toluene, phenol, aniline, benzoic acid, and anisole in particular are very important. So those are things that will name the compound something different. Okay, so we need to pay attention to that when we're doing nomenclature and reading our benzenes. Also, if you have 2 substituents, we now have a way to do it. We can call it instead 1, 2, 1, 3, or 1, 4 as we go around the ring, or we can call them ortho for 1, 2, meta for 1, 3, para for 1, 4. I think one of the cool things about the benzene chapter is we only have one mechanism for everything, but we can do a lot of different things with there. We can add chlorine to our system, but we have to use a catalyst. We can add bromine to it. We have to use a similar catalyst. It just has to be the iron tribromide. That's the only change that we would have to put a bromine there. We don't do fluorine or chlorine. I'm sorry, fluorine or iodine. We can only do the bromine and the chlorine this way. We can also put a nitro group on there if we use a strong acid like this. We can put a sulfate on there if we use a strong acid. And then we have 2 ways of adding a carbon-carbon bond to our system. The first one is called alkylation, and it goes through making a carbocation on a carbon system. That then this is our electrophile, and that's the part that's going to react with the ring. And we also need to think about what things are activators and what things are deactivators. So, and ortho and para direction. For example, chlorine, slightly deactivating, but an ortho para director. Strongly deactivating and a meta director. Okay, so don't forget the direction and or the activation and deactivation. The other form of a carbon-carbon bond we can make is called an acylation. It always makes a ketone, okay? And these reactions actually run a little bit cleaner because once you put one on there, it deactivates the ring. Carbonyl compounds deactivate the ring. Anything with a positive or partially positive charge on it deactivates the ring and gives it a meta direction. So that means once we put one of these alkyl groups on here, it doesn't deactivate the ring at all. It can then react again. So if you want to be very careful and only put one thing on there, it might be better to do the acylation because it stops after one addition. Okay, let's see what we have. And they all have the exact same mechanism. We're going to do something to create a positive charge. Okay. Once we create that positive charge, we usually use a catalyst to do it. In the carbons, we use aluminum trichloride. In the halogens, we use iron trichloride. And with the nitration and the sulfonation, we used sulfuric acid as our activator. Okay. So we activate our system, and then what we do is we have the electrons from the benzene ring act as a nucleophile to create a bond. And then by resonance, we rotate this positive charge around the ring until we use the electrons from this hydrogen and kick out hydrogen as our last step. Okay. So remember where these things go around in this ring, because that gives us our idea about why orthopara-direction works. Okay, so let's talk about remembering activators and directors. Okay, so the general theme on activators and directors is if it has a lone pair, it's strongly activating and it's an orthopara-director. Okay, if it has a lone pair but a slightly electron withdrawing group on it, these carbonyls here, it's still an activator, not as strong, and it's still an orthopara-director. If it's a carbon of aromatic or aliphatic nature, it's weakly activating and an orthopara-director. Okay, these are officially weakly deactivating because of the inductive effect, the fact that they're electronegative, pulling some of the electron density away from the benzene ring, but they're activators, they're orthopara-directors because of the lone pair. So the lone pair is telling us a lot about ortho and para direction on our benzene rings. Okay. Now, in contrast, all the carbonyl compounds bonded directly to our ring are all deactivators. Okay, and including if we did the sulfur here, you can think of this as the sulfur analog of a carbonyl. It's a deactivator. Now, the strong deactivators are the ones that have a permanent positive charge right next to the benzene ring. And this has most of a positive charge because of the inductive effect of having 3 halogens on there. But both of these have a formal positive charge. That's why it's strongly deactivating. All of these moderate to strongly deactivating are meta-directors. These are deactivating, but the lone pairs make them orthopara-directors. All right, so knowing that is kind of important. Amines, very short chapter, but we had some differences here. We had an aliphatic amine, which only has alkyl groups. We have an aromatic amine, which is an amine on an aromatic ring. Then we had a heterocyclic amine, where the amine, the nitrogen was in the ring. And then we had our aromatic heterocyclic amine, where some of the electrons from the nitrogen are contributing to the aromaticity of the system. Excuse me. So the other thing we learned about this is about basicity. The aliphatic amines are more basic than the aromatic amines, and the aromatic amines can shift depending on what's attached to the benzene ring. A strong electron donator changes the ability of those electrons to be used and become less basic. A strong electron drawer makes them become less basic. A strong donator makes them become more basic. Okay. Now, all of the aromatic amines are weaker bases than their aliphatic amines. And the other thing is the bond strength between the nitrogen and the hydrogen is less polar than that for water, and therefore it doesn't hydrogen bond as much. But hydrogen bonding does play a role in bringing the boiling point up a little bit, but not as high as in the case of water or alcohols. Okay, so the last thing we did was spectroscopy. And this picture right here, I did it again. This is the one slide that explains most of spectroscopy for me. The first thing you do in IR spectroscopy is you find types of bonds, not functional groups, not the answers to everything. You're finding the types of bonds. And we have these 4 regions we care about. The light hydrogen atoms right here highest frequency because the atom is so light, highest frequency section. Then our triple bonds are stronger, so they're going to have the next highest frequency, followed by our double bonds and our single bonds. The most useful identification is above 1500. So you're looking for the presence or absence of the functional group. What if I said, I have this, do I have this compound in my system, and the spectrum looked like this? You'd immediately say, wait a minute, this functional group is completely absent. It can't be that compound. But if I showed you another spectrum and it had a peak here, you could say it can be that compound. I have to look for the other peaks. I have to look for those carbon-carbon double bonds and the hydrogens that are above 3000 for the benzene ring. Okay, so you're looking for the presence and absence of peaks when we're talking about IR. Okay. And then when we're talking about NMR, proton is the harder one because we have to worry about spin-spin coupling. But we're looking at the number of peaks. How many unique types of hydrogen do we have? We look at the intensity of the peak. If we do an interval, average, added up all the area under those peaks, we would have a relative intensity. And so if you had 2 hydrogens on one of them and 3 hydrogens on another, our intensity should be that relative ratio of 2 to 3. Then we had position. Position shifts when we had more electronegative atoms. You get further away from 0, you get further downfield. And then spin-spin splitting. That's the hard part. You have to look at how many hydrogens are at 3 bonds away from your peak of interest. And we're going to take that number of hydrogens plus the 1, because that's the peak we're talking about. The other hydrogens are going to split it n times. And so we're looking for the number of hydrogens within 3 bonds plus 1. And that should give you the type of splitting we have. Okay. So when we look at our spectrum, we have our chemical shift going this way. So that's position. We have our relative intensity here. But because the peaks are split, we have to add up all of them and get our relative intensity. And we could do 2 to 3, let's say, okay? And so then we're looking for splitting right here. We have this peak right here has 3 hydrogens within 3 bonds of there. So this should give us 4 peaks. We have, if we look at the other one right here, it has 2 hydrogens within 3 peaks, and it has 1 peak for itself. So it's going to have 3 peaks. Okay, so that means this one's B because of the 3 peaks, and this one's A because of the 4 peaks. Sometimes you might think that, oh, I can tell by shift, or you want to put all of the pieces together. You want to look at that intensity, you want to look at the splitting, and you want to look at the shift. Okay. And that'll help you identify them. Even if you get like the intensity wrong on one or the position wrong on one, the splitting is going to tell you which is which. Okay. And then as we learned today, carbon's a little bit simple. All we have to do is worry about how many peaks we have, not forgetting our carbonyls. We ignored them in proton NMR. But how many unique, and then the relative position. The relative shift downfield is the same for both proton and carbon NMR. And that gives us our right here. Okay. So, and I think the homework problems for this particular chapter are are about the same complexity as what I discussed in class. Okay. And that is that is chapter 11. Questions about what to think about when we're doing or one of the other chapters that I didn't cover here. Okay, well, what I'm going to do now is I'm going to go ahead and stop recording. And if you want to stay back and ask questions, that'll be fine. If not, well, I'll just convert this into a video and upload it to YouTube. Okay, let me stop recording.